Today is about what arithmetic rules survive when numbers become matrices. Many rules still work, but matrix multiplication has attitude. It does not commute, and it can even be undefined. We also introduce identity matrices, inverses, and a few key transpose and inverse facts that we will use all semester. Think of this as matrix common sense. You will learn the rules that always work and the traps that look like real number algebra but fail for matrices. If you keep the rules straight, later topics like inverses and diagonalization become much easier. The biggest mindset shift is this: for matrices, order matters. You cannot casually swap factors the way you do with real numbers. When in doubt, check sizes first, then compute carefully. Most good algebra laws still work. Addition behaves nicely, multiplication is associative, and distributive laws work. The key hidden rule is sizes must allow the operations. Matrices are polite about rules, but strict about dimensions. Matrix addition is boring in a good way. It is just entry-wise addition. So the proof reduces to the fact that real numbers satisfy a plus b equals b plus a. This is the standard template. Same size, then show entries match. The magic is not magic. It is just distributivity of real numbers inside the summation. Associative means you can parenthesize however you like, but you cannot reorder factors. This matters a lot for computation. You often choose parentheses to make the work easier. The zero matrix behaves like the number 0 in many ways. Just remember, the symbol O depends on context because its size must match the situation. These two failures are big deals. They explain why matrix algebra needs its own logic, especially when solving equations. Never divide by a matrix unless you truly have an inverse. Over real numbers you would cancel A immediately. With matrices, that move is illegal unless A has an inverse and you multiply by it correctly. So, product equals 0 does not automatically tell you one factor is 0. Matrices can destroy information in a way real numbers cannot. Identity matrices are the number one of matrix multiplication. The subscripts matter. Left identity size matches rows, right identity size matches columns. This is a very useful test later. For a square matrix, RREF equals identity is the signature of being invertible. Invertible means you can undo the action of A. The definition requires both sides, AB equals I and BA equals I. For square matrices, A correct inverse automatically works on both sides, but the definition keeps it honest. This is a great habit. Always multiply both ways when you are learning. It catches arithmetic slips and reinforces that matrix multiplication cares about order. Identity matrices have no zero rows or columns. So if A has a zero row or column, it can never turn into the identity by multiplication. This is reassuring. If an inverse exists, it is the inverse. So choosing a symbol like A inverse makes sense. This formula is a fast tool for 2 by 2 matrices. The condition add minus BC not equal to 0 is the permission slip that the inverse exists. This is the cleanest style for a first course. Guess the inverse, then verify it. The only thing you must remember is, the denominator add minus BC cannot be 0. In class, I would first compute add minus BC. If it is 0, stop, no inverse. If it is non-zero, plug into the formula and simplify carefully. This is a nice theoretical method, especially for small systems. For bigger systems, Gaussian elimination is usually faster and more stable. This example is a perfect proof of concept. You see exactly how inverses connect to solving linear systems. The reverse order is not optional. Inverses are like undo buttons. You must undo the last action first. This is good practice for managing order. If you ever write A inverse B inverse instead of B inverse A inverse, this example will punish you immediately. The exponent rules look familiar, and they mostly behave. The key condition is still invertibility when you use negative powers. In practice, find A inverse first, then cube it for A to the minus 3. And for 4A, the inverse is 1/4 times A inverse. This is plugging a matrix into a polynomial. You replace x with a and the constant term with a multiple of the identity. The most important one to remember is the last one. Transpose flips the order of multiplication, like a mirror that also reverses the line. Again, the proof is entry-wise. Matrix identities usually reduce to simple real number identities once you look at one entry. This is a great check because it is small enough to compute directly. It also reinforces that transpose reverses order. This identity is extremely useful. It lets you move transpose and inverse past each other safely, as long as you keep the order correct. The method is always the same. Peel factors off one at a time using inverses. The main danger is flipping the order by accident. Treat it like undoing a chain of actions. Undo the last thing first. The big takeaways. Matrix multiplication is not commutative, cancellation can fail, and even a zero product does not force a zero factor. Identity and inverses behave like one and reciprocals, but order matters everywhere.